Thank you. So let's change a little bit the perspective here. A little bit, we change the point of view. From the point of view of computer scientist, I will try to move a little bit to the point of view of computational physicists, as we are. These considerations are outcome from different works we did in collaboration, of course, with Thierry and Brice and other people in our community, related to how to investigate and interpret performance issues and performance opportunities in view of exascale applications in the context of electronic structure calculations. So, to introduce a little bit these contexts, we are computational physicists working in material science, and essentially the software codes I am referring to while talking about these applications is is under the name of density functional theory codes. In particular, our experience comes from the development and implementation of a density functional theory code named BigDFT, of which we have already seen some slides in Brice's previous talk. This is a project which started more than 10 years ago now. The idea was to build from scratch a density functional theory code conceived for supercomputers, so already in the aim of high performance computing, based on a new kind of basis set, which was not deeply used in the community since then, which is under the name of Daubechies wavelet. So this adventure started 10 years ago, as I said, gave us the opportunity to gather different experiences and to get several know-how about the future opportunities that an high-performance computing environment might provide to us. But let's recall that we are, first of all, computational physicists, so our job is to provide scientific papers in material science community. So all the codes which work in this context, density functional theory code, have as principal aim the production calculations. What are production calculations? Are simply the calculations you have to run to extract your scientific data and to publish paper with. So if now one has give a look at what means a production computation, a typical production computation in the general framework of DFT, not only related to BigDFT at all, it's generally related to density functional theory computations in the standard context. So we might see that high performance computing and DFT are not, let's say, directly built to match together. I like to say that there are no letters in common between DFT and HPC. And the reason is that if one has a look at what happens in the runtime of a DFT code, one might see that peak performance is really far from being reached. And there are a lot of reasons for that. I will try to explain some of them in the following slide. The point, indeed, is that exaflop for DFT codes is not a thing which has to be reached in terms of peak performance. It's rather an opportunity to get new physics by using bigger machines. So it is very important to keep this in mind, because it is not only a matter of reaching high level of number crunching. This is not necessarily possible in the DFT community. The point is that exaflop is the usage of a very big machine in an efficient way, which allows you the possibility of obtaining new physics. So exaflop can be done in a DFT paradigm, in an electronic structure computation paradigm, but one has to take care of some particular points which are related to the behavior of your code in a large machine. I will try to give you some examples in this occasion. Well, the main reason why DFT is, or at least a single instance of a DFT code is difficult to parallelize at intensive parallel level, is that the workflow for a typical DFT code in the context of the presentation of Olivier we saw this morning, is a very simple workflow. Actually, the self-consistent cycle, there is an iterative cycle in a typical DFT code, is built by a lot of homogeneous and regular tasks, if we use the language of task programming, which we have seen before. So a typical DFT code has a simple workflow which is full of lot of global and blocking communication. Still, there are a lot of things which can be done to exploit an HPC framework in this context. But first, one has to take care of this point. The DFT code is essentially a data treatment code, at least for the class of codes which belongs to what is called the systematic basis sets, like plane waves, wavelets are an example, and finite differences, and so forth. So the main reason is that transferring data now costs more than calculating data. And as the amount of data in a DFT cycle is always constant, essentially one might think that DFT are data processing code. So they still have kernels which are bandwidth bound. So they are limited by the bandwidth of your machine. So this is a problem which has to be also considered in the context of analyzing the performance of a DFT code. So let's give some example to make the discussion clearer, if possible. So BigDFT is a code which uses Daubechies wavelets. So one has to map operators in the Concham DFT, whatever it means, into a computer kernel. In BigDFT, the computing kernels which are associated to these operators are short and separable convolutions, which essentially are very similar to, let's say, image processing convolutions. But the situation might be analyzed in a similar manner also for plane waves code, which instead of convolutions here of this kind use FFTs, fast Fourier transforms, to process the data. So for a run of BigDFT, one might investigate the amount of time which is spent into the different kernels. For a normal run, for a typical run of one of the kind I have mentioned before, one might say that there is what it is easily can be identified as a hotspot operation. The purple line here is essentially the time which, the percentage of the time which is spent in the convolution. Now, there is a first point. I have said bandwidth limited code, and that this is a very common situation for computer physicists, let's say computational physicists. So one might see that here in these histograms I showed the wall time spent into different runs of BigDFT by increasing the number of MPI tasks which are on my calculation nodes. And the amount of time spent in the communication is negligible with respect to the overall time. You don't see let's say category which is visible in these within these let's say pattern. So still the parallel efficiency is not 100%. So that's another thing which should not surprise you if you are really aware of this problem of bandwidth. Even though you perfectly cut your job into regular tasks, all of them treating the same amount of data, and you do not spend time in communicating, you do not have 100% parallel efficiency. Why? Because you are reaching your bandwidth limit. The data which you have to treat is not such that it is so big that it cannot be treated in the same time. So you have a bandwidth problem, and this actually, essentially, there is nothing that can be done at this level. All it is regular, 100% CPUs, that's simply life. But this doesn't mean that the situation is, let's say, doomed. You can do a lot of things on this starting point. First of all, you have seen that there is a hotspot operation. So optimization is something which can be performed to reduce the amount of time spent in the communication by using techniques like boastifications of these convolutions. We did it in collaboration with Brice. Usage of GPU acceleration, OpenCL, we did it in the early 2010. So let's discuss a little bit the considerations which arise on these bases. Another point is, of course, shared memory parallelization. So OpenMP in conjunction with MPI. Here, in the problem of bandwidth is even more evident because you have to take care of the fact that in a shared memory parallelization, thread concurrency might become huge. Now there are examples of BigDFT runs in production where each node has 64 OpenMP thread working concurrently, like for example the runs which regularly run in BlueGeneQ machines, Turing machine or Mira machine at Argonne in the US. But if you are still in a situation where you have a hotspot operation, and this is a situation which is advantageous, you might use GPUs to reduce this purple curve here, just by accelerating the convolution kernels or the DFTs, or depending on which is the main basis set you use in your DFT code, and you might achieve speed-ups which are very interesting. So by using GPU, in our case we used OpenCL. The idea, as Brice discussed, is also to move into the direction of boastifications of these kernels within the aim, within the context of GPU acceleration. Well, for some kind of systems, you can get speed-ups which are few orders of magnitudes. So you really can do new physics. You can explore new spaces in your research thanks to this approach. But now, so that was the situation in the early 2010. So BigDFT was a code which was conceived with the 3 levels of parallelization. So MPI, OpenMP, GPU at the same level. We did that in 2009. Actually, it was award-winning work. It was awarded by the Bull-Fourier Prize in 2009, I think. Still, there is a problem because our code was limited by the number of atoms, by the scaling with respect to the number of atoms. So let's remind the original aim, doing new physics. Well, if you want to do new physics by increasing the number of atoms, of course, at first sight, it seems to be a good way to exploit exascale, but still, you have the problem that if you double the size of your system, your execution time, it takes a factor of 8. And then new physics, it may be possible, but it becomes more and more difficult to increase the size of the system. And then this is when the computational physicists, let's say, take a role in the exploitation of HPC context. We had to change the algorithm of the code, so a deep modification of the code in the context where the number of atoms is bigger, larger than, let's say, a few hundred atoms. So in BigDFT there is also another approach which uses the same kernel. This approach uses the same kernel, but in a completely different way. So, to make a long story short, we actually move towards an approach which is linearly scaling with respect to the number of atoms. Within this approach, you use the same kernels, but with another parallelization scheme, another percentage of the usage of the scheme. You can do the same physics, but in a way which is completely different from a computational, from a computer science point of view, because you don't have anymore a hotspot operation. Your algorithm is different, and your parallel scheduling is not anymore homogeneous. So we reach a situation where the tasks is not are not scheduled within a simple workflow as before. So this is a slide which I can skip. I think the point is that you can reduce wall time. So computational physicists is happier now because you can do bigger systems in lower wall time. But the point is that you have completely changed the scenario. On the same computer, you now have an even lower number of flops per atom. So peak performance is even more far than before. You have a different communication scheduling. you don't have any more hotspot operation, so there are extra complexities which are arising in the context of a newly conceived algorithm. Well, one might say that these extra complexities are indeed extra opportunities which arise in the context of HPC, because, as I said, as the wall time is lower, new science is possible. So that is the way in which exascale has to be thought, not just filling the machine with high number crunching for doing a similar physics, but just having new opportunities where the filling of the machine is maybe even more difficult, but still new physics and new science is now accessible. So the point is exactly that, and this is the considerations I would like to share with you today, essentially, is that the same executable, so the same BigDFT executable in our case, but there are similar situations in also other codes in our community, may have a completely different runtime properties by just changing the input file. So you have one machine, one executable which is compiled, for which this machine is compiled. You just change your input file a while. For those who knows what I mean, you just change, for example, the exchange or correlation approximation, and your runtime is now completely different. All the considerations you have done in the context of one input file are now maybe dramatically changed. So the optimization strategy also, in view of the usage of a DFT, have to be adapted to the physical problem you want to simulate. You can't do optimization strategy before. Therefore, you can't simply delegate the approach of optimizations to someone which is not aware of the algorithmic complexity which is below your code. So the practical consideration is that the instrumentation of your code has to be carried out in production. So you really have to invest to put in practical terms the fact that you have to profile your code each time you run it. Of course, your profiling should not deeply interfere with your execution. You don't have to, for example, compile your code with some low performance debugging tool because you want to do new science with. But the point is that if you don't profile your code in production, you may not understand. You may end to be in a situation where you don't understand why your performance are not anymore as you expected. So, in our experience, these are the things which I would like to show in the last part of this talk. We put some non-intrusive, or at least less intrusive as possible, profiling tool in our code. We built these tools based on markup languages. We have identified a markup language dialect which might be of high, let's say, interest potentially in our community. Let's discuss about that in a while. The point is that this profiling is not profiling only one kernel, but it is profiling a set of kernels which are associated to the algorithm we use, which is identified by the developer. So it is as if you are building your own profiler for your code that helps you in understanding what are the benefits of changing or not the algorithm in your execution. I have some examples to show you this feature in a few minutes. So the markup language we have identified is block structured YAML. YAML is a markup language which has this, let's say, appearance. If you don't have heard about that, it is really like JSON. If you know what JSON is, the advantage of this markup language is that it is a markup language which is both human and computer readable, and therefore it's optimal for configuration files, for something which can be at the same time hand-tuned by the user, but also generated automatically by the machine. It is not like the XML approach where, of course, for the computer this is really easy to handle, but for the user it might be a little bit less complicated due to, let's say, aesthetic reasons. So this markup language is the way in which we conceive the input-output of BigDFT. So we are in the situation where you have input files like that, the log files of the run and the log files associated to the timing of your runs come out in this format. And you end up with a situation where you might analyze these log files and inspect performance consideration after you did your production runs without having to rerun your executable. So to give you an example, I think that the best thing is now to move to something, to something more practical. Here there is some thing which simply takes the outcome of a big DFT run and provides you with some data. So imagine you did, this is a system of an 80 atom of boron, it's a cluster of 80 atom of boron, whatever it means, it's a cage like a fullerene. So these are runs which are made on the same system with different repartitions of MPI and OpenMP. What can be see there is that each of the run is separated in categories which are associated really to the algorithm which is behind each of these categories. No profiler or debuggers can provide you with this information because this information is an information which is somehow tailored for the developer. So it's really the developer which decided which are the kernels which go in the category of the convolutions. And for example, here for the convolutions, you may see that all these kernels are somehow belonging to these categories. So this is something which is built at runtime by your code in a low profiling, not really intrusive way. Here you might see that also this profiler is actually profiling itself. So you might see that the time you spent in profiling your routines is of the order of few percent of your overall run. It is somehow something, so these are basically matplotlib routines. You might quantify in percent is less than 0.1%. So also in this case you might have informations about your runtime. And then if one wants, this is the spirit, but now let's come to some practical example. Here, for example, you have another set of runs. So you see that you increase your number of MPI, you can inspect here again, there is an hotspot operations. So you might see convolutions are indeed the best, the most time consuming part of your run. These are runs of BigDFT on ARM architecture, for example, which is something which we did with Brice in 1 to 2 years ago, as far as I remember. So what happens here is that in percent, you see that the parallel efficiency is very good, more than 97%. So you know that you can increase your number of MPI for this system at a glance. The advantage is what? Is that you can also investigate what are potential performance issues on your machine. At the same moment in which you run, you have the load balancing of different categories, for example, of your run, which are still developer tailored categories. They are not anymore just MPI send, MPI receive performance, but they are really based on your approach. And you may see that there is a node on this system. This is something which happens fast, this happens more often than one might believe. In this system, there was a node which was not really performing well about communication. Even though the task repartitions of the system was completely regular, it is just a problem of runtime on this machine. By a tool like that, you can detect what is the problem. It happened to us a few times that we just, thanks to tools like that, we may write on the systems administrators and say, well, your node number 128, there is some parasite process and it is taking more time than expected. Only by profiling your code in production and analyzing with a lightweight language like YAML, for example, your runtime, you might inspect some non-ideal situations like these ones. So these are, let's say, daily life problem while producing new physics, and they are not based on prototype runs. Another example, I think is the second last example here. These are two runs of BigDFT on the same system, but one is done with, so again, here you might see, well, this is afterward. One is done with the cubic scaling BigDFT part. So the previously done code, and then is the with the linear scaling part. So here you can see that the percentage is completely different. If you optimize the convolutions, even with both here, you may not gain a lot of time here, because it is not a hotspot operation anymore. And this is the same executable. These are the same systems. You just change one keyword in your input file. And you may exploit or not the work of a pool of computer scientists which may have developed for you a very efficient way of this blue zone. But if you change your input file, you may be in a situation where you cannot exploit that. So I think that this is the essential part I would like to show you today. And do not hesitate to come to us and to ask questions if you are interested. Thank you very much.